Welcome to another stats research seminar. Today we have the pleasure of welcoming Claire Donnat from University of Chicago. We'll be giving a talk on sparse topic modeling via spectral decomposition and thresholding. So I hope you will all join me in welcoming Claire. Before we start, so Claire is an assistant professor in the Department of Statistics at the University of Chicago. She obtained her PhD in statistics from Stanford in 2020, where she worked with Professor Susan Holmes. Her work focuses on statistical estimation in high dimensions with structure, typically encoded by a graph. So I hope you all enjoy this talk. If you have questions, please raise your hand and Claire will call on you to ask the question. If you're on Zoom, you can also raise your hand. I'll be monitoring that. That's it. Thank you.
All right. Well, thank you very much for the invitation and thank you very much for coming to this talk. So the plan today is to talk a little bit about topic modeling and some of the work that we've been getting into actually over the past year with, in general, the idea of adding structure in the topic estimation. So specifically today, I'll talk about adding sparsity. Yes, so just to begin with a little bit of context. So topic modeling is a widespread data modeling technique. So usually the setting is as follows. Suppose you observe a corpus of documents. So here I have 3. And the idea is that these different documents actually come from, well, each of them have a set of topics that can be associated with them, right? So here, for instance, in document 1, I have a recipe. So let's say it's topic cooking. Document 2 is just a weather report. So let's say topic weather. In document 3 is a piece of news. And here we could say it's going to be society and entertainment. So in topic modeling, essentially what we want to do is in an unsupervised fashion, detect what are the different topics in our corpus of documents. So from a data modeling perspective, the data that you might be observing is as follows. So each row here of this data matrix is a document, and the columns are the different words. And essentially what we're representing here, the documents by, is so the different entries of this matrix here would represent the number of a given word that has been observed in that particular document, right? So it's a bag of words model, right? We're just essentially counting occurrences of words across the different documents. And when we say we want to try to recover topics here, what do we actually mean? A topic is going to be defined as a distribution over word frequencies. The idea being that if I'm describing the topic weather, certain words such as showers or rain occur with a certain frequency that is non-negative, right? And that frequency might be different in another topic, such as, for instance, cooking, where that probability might actually be closer to 0. Right? So that's essentially the matrix, one of the matrix that we need to estimate of interest to us. The other thing that you might also be interested in is the topic assignment matrix. That is to say, for each document, what are the topics that this, this document can actually be described as, right? So here, for instance, it is important to stress that these the documents can come from a mixture of different topics, right? It's not just one. It's essentially almost like a soft clustering method, if you will. So this is all good, right? So you could say this is an interesting model, why not? But in this day and age, especially with ChatGPT and the like, right? NLP is a difficult, if not dangerous, research direction to get into. So why do we actually care about these topic models? That seems sort of, like my representation of the data is very simple. And so why do we care about these estimators? Well, the thing that's interesting about these different topic models is that the applications actually of this model go beyond NLP. These models have actually been successfully applied in fields like genomics, microbiome studies, e-commerce, spatial transcriptomics. And what's interesting there is that the data regime that these applications typically employ is quite different from the standard NLP setting, right? So what works in NLP might not necessarily generalize for these types of applications. And when I say data regime, I mean, for instance, the number of documents, the number of words per documents, the size of a vocabulary, right? So all of these, as we'll see, have an impact actually on the ease of estimation of our topics. So in particular, right, because I'm going to try to show this is perhaps data regimes are a bit different and perhaps a bit harder than NLP, right? We'll typically need to add structure. To show you an example of, like, this is actually the example that got us started into topic modeling in the first place when we read about it last year. We're going to consider the special case of spatial transcriptomics, actually. So in spatial transcriptomics, so certain imaging technologies actually allow us now to have access to a lot of information about the way the different cells, essentially, and especially the immune cells, are organized within a tissue sample. So here's, for instance, a different tissue sample. And what's great about the current imaging technologies is that we actually have the possibility now of sort of, well, first observing the different cells and actually recognizing what kind of cell type this cell belongs to, right? So, or is the particular cell of interest. And this is great because now we have essentially spatial structure on the sample. And a question of interest in immunology is, well, can we actually use this information to try to understand how the immune system, for instance, reacts first, with each other, right? All the cells interact with one another and with the immune cell. And there's actually some amount of evidence that the tumor immune environment has been linked essentially, right, with certain outcomes, so like survival or length of survival, etc. So there's growing interest in the community to sort of understand essentially this tumor environment and these different spatial interactions between cells. And one way of doing it is actually through topic modeling, right? So this paper in 2020 by Chen et al. Proposes essentially the following. So to try to get to local interactions, what they actually do is partition the slide essentially into smaller microenvironments, right? So here essentially I'm partitioning in these local bins, if you will, right? Each bin is going to be my document. I count the number of the cells of different types that I observe, and these are my words, right? So now the data that I observe essentially is exactly as before, right? So each row here is a microenvironment, and the entries here, the columns are the different cell types. And essentially what the authors propose here is to understand the different tumor microenvironments by looking at, finding topics essentially amongst these tumor environments. Now, this is a difficult, well, first, let me show you how they intend to use it. The idea is to get to a plot like this at the end, right? Where you have essentially, so here I think it's from the screen of mice, of different mice. And what you want to do is essentially try to recognize the different topics, right? And color essentially to try to extract structure from this data. And what they will try to do then is also essentially correlate certain topics with an outcome of interest, like let's say survival, right? So now, this seems like a laudable goal. The reason why it's a bit difficult in this particular setting is because of the essentially the data regime. So in this particular application, for instance, so the number of documents, the microenvironments, the tumor microenvironments that you have is actually large, right? So you have multiple of them. The size of the dictionary is relatively small, but the number of words per document is also really small. So we're talking an average about, maybe 11 cells per document. And intuitively, it makes sense that if you have very few words per document, it's hard to infer the topic. And so this is where the whole idea of integrated structure comes into, right? In this particular setting, you might say, okay, well, maybe each document has few words, but it makes sense to assume that perhaps nearby documents or nearby tumor microenvironments, if you will, have similar structure, have similar topic composition, right? So essentially, you're essentially pooling information by assuming some sort of spatial coherence, right? So this is the type of structure that the authors assume. You could also assume that, something that could help you would be that maybe each document has very few topics, for instance, right? So some notion of sparsity. So this is typically an example of a setting where topic modeling needs to be helped. Essentially, you need to add structure to help estimation, but different types of structure could actually help. So that's essentially our setting. So let's now look a little bit at literature. How do you actually fit a topic model? So there are essentially two main ways in which you could approach the problem. One is through a Bayesian perspective. So that's the latent directly allocation proposed by Bly et al. 20 years ago. And so this is a topic model, a topic model through a Bayesian essential perspective. So to try to understand it a little bit, let's try to detail a bit the generative model. So to generate a document, well, first you'd have to generate essentially the topic word distribution, or the word frequency distribution per topic, so usually from a Dirichlet distribution. Then for each document, you'd have to specify first its topic assignment. So what is this document? What topics does it comprise? So for instance, let's say I sample and I have 4 topics here. I sample 30% of topic 1 and 70% of topic 2 and 0 for the rest. And then for generating the actual document here, you could first think as your N words that you have in your document as just for the moment placeholders, and you're going to have to fill them. And the way you would fill them is by saying, well, first for each word, sample a topic from that topic assignment matrix. right? So here, 30% topic one, 30% of chances it will be a word coming from topic one and 70 from topic two. So essentially you sample. Once you have your topic, you essentially look within the word frequency distribution for that particular topic. What is a good candidate word for that placeholder, you fill it in, and you essentially iterate for the rest of the word. So I hope this sort of, this generative model sort of makes sense at least. Okay, so that's essentially a Bayesian the Bayesian perspective. From a frequency approach, you could say, right? From if you didn't want to actually put Bayesian priors for the parameters of interest or variables of interest, you could try to apply instead the probabilistic latent semantic indexing technique, right? So here, essentially, the idea is the following. So there's actually usually they essentially translate the matrix, or sorry, transpose the matrix such that the documents are actually in the columns and the words are in the rows. But essentially what this is saying is that each document that you see is essentially a multinomial distribution, right? So each document is independently distributed from a normal multinomial distribution. This is the number of words that you have to generate. And the underlying essentially frequency for that particular document is denoted by this frequency matrix D0. And the thing that essentially saves us in this setting is that we're going to assume that the underlying frequency matrix D0 has lowering structure. Here indicated by D0 equals A times W, where you are also going to assume that, so essentially all of the columns of A sum up to 1, and here the columns of W also sum up to 1. So you have some essentially simplex structure on A and W, right? So essentially at the end of the day, so the interpretation is very similar to LDA, right? So you can interpret essentially the entry of matrix AJK here, so JK, as the probability of seeing word J given topic K, and for the entry of the matrix W here, entry KI, so that's the probability of seeing topic K given document I. Okay, so essentially it's very similar to the Bayesian setting, except these are fixed matrices, right? So a little bit of let's push a little bit the comparison. So when we started looking essentially at these different ways of fitting topic models, we wanted to try to understand essentially what people were using them for, and what were the differences. So in particular, from a usage perspective, so beyond the fact that one is perhaps a fixed matrix and the other essentially tries to estimate random variables, it seemed that in the literature, at least the way people were using them, LDA seemed to be the practitioner's favorite, and that's a lot of applied papers when they want to apply essentially one of these topic modeling techniques would prefer LDA, whereas there seems to be, especially recently, a certain amount of interest for PLSI, especially because at the end of the day, it's just linear algebra and it's a little bit easier to analyze theoretically. So the reason that we could think about for LDA being essentially the practitioner's favorite was that, well, there are a couple of candidate reasons, really. One of them is that the prediction of a new document is way easier in LDA than in PLSI. PLSI actually had to refit the entire model, right, to estimate the topic distribution of a new document. But in LDA, one of the main things is, well, first of all, it looks like sometimes the estimates are a little bit more robust, right? It's a little less fragile, which is important. And the second thing is that, it's perhaps more amenable to tweaking, essentially, right? Once, if you have a structure, if you're assuming that your estimator has a structure, right? For instance, spatial cohesion or maybe sparsity, it's usually quite easy to go in RStan and essentially try to tweak a little bit the prior, right? To try to essentially gear or guide the estimator towards that particular structure. Whereas PLSI technique are seem a little bit more rigid, right? So that's a little bit of a pity, because when you look at the details, PLSI are essentially SVD based, right? And that can be quite fast, right? And you can have less problems with, for instance, like LDA sometimes has conversion problems, etc. So PLSI is great potential, but that seems a little bit undeveloped, right? So the question for today's talk essentially is the question that we try to ask ourselves as we're trying to get into this problem, right? So first of all, what are the known theoretical guarantees of the PLSI algorithms? And so what is the state of the art? and why can we understand essentially their frailties? And the second is, can we actually leverage known additional structure in the data to try to improve upon these estimators, right? So in particular, so I've talked about spatial coherence in that specific example, but we're going to focus today on sparsity because we're trying to get here. But first, we needed to essentially do the simpler task, essentially, of the sparsity, the sparsity course, essentially. So I'll talk today about this. All right, so first, let's start with an introduction to PLSI models. So in general, in PLSI, a somehow ubiquitous assumption that you're essentially, that you're hoping holds actually, is that there exists a word J for topic K such that AJK is greater than 0, is strictly non-zero, right? So strictly positive, but AJK prime is actually 0 for all K that are, for all other Ks, right? For all K prime that are in the rest of the this set K without the one that is non-zero. And essentially what this means is that there exists a word that is pure. It's only found in one topic. So for instance, here I have an example of such a pure word, right, in the first 3 rows. That assumption actually was, I think, postulated by Donnat in the early 2000s, is a sufficient but not necessary assumption for essentially identifiability of your PLSI model. Now, essentially, this assumption also gives rise to a number of algorithms, right? And I essentially put some reference here to show that it's somehow, the way that all the algorithms are trying to approach the problem. The idea is that you first have to identify anchor words for each topic as a first step. And once you have the anchor words, you can typically recover the topics, and I'll get into the detail of that in just a second, right? That is always sort of the same method, right? These anchor words are essentially the thing that you estimate first, and then you recover the topics. So in particular, today, I want to talk a little bit more about a recent method for doing this, right, that essentially is based on the same premise, right? So first cover the anchor words and then estimate the rest. And that is the method called topic score by Ko et al. From 2022. This method is particularly interesting because it's one of the first and only methods that has essentially statistical guarantees, right? That try to go into the theory to try to derive essentially bounds, minimax bounds, and upper bounds for the estimation error. So the idea in topic score is that you first start with a pre-normalization of the matrix D. So D here is your data matrix. So we have to remember that essentially this is the columns are the documents here, and the rows are the words. And the idea is that here you start, so you start by first dividing essentially by the frequency of the word, right? The overall magnitude of the word, right? So the number of times it appears. This essentially is supposed to, if you think about words, they have very different frequencies, right? So this pre-SVD normalization is supposed to essentially put words on similar footing, if you will, right? Deal with the high frequency heterogeneity that you typically observe in text data. Once you have this, right, so let's say it's just pre-SVD normalization, the second step is to do an SVD of the matrix X that you observe, right? So why not, right? So I essentially write X equals U lambda V transpose, where U is a k-dimensional vector. Now, this is where it gets interesting. You can actually show that, so this vector U here, right, this singular value, you can think of it as a word embedding, if you will, right? So it's a vector that represents each word in a k-dimensional space. You can actually show, it's not too complicated, sort of, just essentially just a little bit of algebra, that each of these essentially these points U, right, are actually belong to a simplicial cone, where a simplicial cone is essentially defined by a set of rays, right? So here, and you're saying that each of the points, the U's here are a sets of, are just a linear combination of these rays, where the coefficients of that linear combination are actually non-negative, right? And what's great as well is you can actually show that the anchor words are actually located on the rays, right? Now, so that's an interesting properties actually of this eigenvector decomposition. And but still, a cone is a bit hard to handle, right? So the idea here is that what you do is a post-SVD normalization. More precisely, you take the ratio, you essentially look at the second and up to the k eigenvector, and you divide them entry-wise by the first, right? this you can actually show has the effect of collapsing this cone onto this simplex here. So the idea here is that all of the anchor words here are projected onto the vertices here, and all the coins here are projected essentially inside that simplex here, right? So this is interesting. So by the way, this is a method called SCORE. SCORE stands for spectral clustering on ratios of eigenvectors, right? And it's a method that was originally developed for community detection in degree-corrected stochastic block models. And the idea is that this ratio actually allows you, for the DCSBM case, to get rid of the frequency heterogeneity essentially between, essentially between nodes in a community, right? To allow you to estimate essentially community membership. But it's applied here essentially to get rid essentially of that dimension and collapse everything into a simplex. Okay, so the SCORE method is actually from another author, so Jin in 2015. Should have put the reference. Okay, so you do this post-SVD normalization, and once you have your simplex, essentially, this is where you can do a vertex hunting procedure. So you know that the anchor words, if there are any, right, are on the vertices. Yes. No. Okay. Okay, so well, you can perhaps ask me later if the entire procedure doesn't answer your question. So once you have your, so you know that the anchor words are on the vertices. So what you do typically is you try to recover what these vertices are, right? So you do just a generic, you apply a generic vertex hunting procedure. So I'm not going to go into the details here. For instance, you have several candidates actually for this, right? It's just essentially something that has to do with the point cloud, right? So for instance, you could try to look for things that maximize the L2 norm, the Euclidean norm of these guys, right? To try to select essentially a bunch of vertices. So once you recover essentially these vertices, you try to express the point cloud as a linear combination of these vertices, right? So this you can actually express as this linear combination. So these are vertices. You're trying to express your R here, right, as a linear combination of the vertices. And what's great actually is that once you have this P hat here, it's almost A, right, up to essentially an appropriate scaling, right, because you know that the essentially the columns must sum up to 1. So this is the top explore procedure. Does this make sense? Yes. So the vertex hunting here, we can just think of it as an algorithm that essentially is more generally an algorithm that if you apply it to a point cloud, right, that you assuming has some sort of simplicial structure, will extract these points, right? Yes, exactly, right. Yes, exactly. It's just and there's several candidates, right? There's an entire chunk of the literature on trying to come up with these algorithms. So there's several candidates.
Is it difficult because your simplex maybe like 7.5 on shift, or?
It's not too difficult. In fact, what you hear, right? So there's a number. It depends. So if you have essentially the trick then is you can try to get rid of this anchor word essentially assumption by looking at procedures that don't try to leverage that, right? So just archetypal analysis, for instance, is somehow very related to this problem, right? But yeah, the trickiest part here is to get essentially a good point cloud, right? The difficulty is going to be linked to how good your point cloud is essentially at the end of the day. Does this make sense? Okay. Mm-hmm. Yes. So you can actually show that you can show that the U's here are within a simplicial cone, right? So a simplicial cone is defined by the rays, and actually the anchor words fall on the rays, right? That fall on the rays, yeah. So the vertices on the right are fully determined by the anchor words? Yes, the vertices are the anchor words essentially. So yeah, so because that is the complex fall the anchor. Yeah, yeah. So this is essentially the remarkable part about this algorithm, right? Is that you essentially do an SVD and you tweak it a little bit, right, to get back to essentially a nice point cloud that you can extract vertices from. So a little bit more on the theoretical results of this paper. So the authors actually show, have guarantees as to the, for instance, the estimation error. Note that this is all up to permutation of the topics, right? So I'm just got rid of the permutation here for T. It's all up to permutation. So essentially what this result tells us is that, so you're quantifying your error in terms of the L1 norm. And if essentially you have a high number of words, so n is greater than p at the power 4/3, then your error scales as square root p log n over capital N, where capital N is the length of the document and little n is the number of documents. Okay, now if you have fewer words, actually this error looks like p squared square root p log n over the same. So where this gets a little bit interesting, right, is if you analyze this, is that, well, first of all, the dependency on p is not great, right? So p is the vocabulary size, and so an error that scales as p squared square root p is not particularly great, right? The other thing you could say is that, well, does this make intuitive sense? I don't know, because essentially so suppose, for instance, you have a growing number of documents, just of text, right? As you're increasing the number of documents, essentially you're going to see more rare words, right? So the size of the dictionary is going to grow. But after a while, essentially, you have a good idea, like not all words are relevant for the topic estimation, right? And very rare words, for instance, are not necessarily super relevant for the topics either, right? So essentially, the idea that this error should be that dependent on the dictionary size is not great. Right? You'd expect it after a while to essentially say, well, we have enough words, essentially, like the rest are essentially just, they're essentially relevant, right? So here, no, actually, right? So here, the authors make very few assumptions in this particular work. You have certain assumptions, right? But I'll show them actually because there's a good overlap, right? But yeah, indeed, you need essentially you have essentially some conditions on the matrix A and W, right? That tells you that it's well conditioned, and otherwise estimation is impossible. Yeah. Okay. So the idea that we had was essentially, can we try to prove, use some priors essentially on the structure of the solution to try to improve this estimation, and try in particular to deal with this idea that the dictionary size is a little bit too big here. The essentially dependency of the error bound on the dictionary size is a little too strong. So this essentially leads us to considering essentially the additional works in the literature, right? So some people have tried this idea of exploiting additional structure, so mostly sparsity. So Bing et al., for instance, in 2020, will assume that the number of entries in the matrix A is actually small, and it will lead them to error bounds essentially that look something like this. So it looks actually very similar to one of the bounds that we've seen before, except the dependency on P is replaced here by the number of non-zero entries of A. Yes.
So what norm is the matrix from here? Is this like on the vectorized matrix, or is this like
just the L1 norm of essentially the difference, the L1 norm of the differences, right?
So you treated it as a vector.
Almost.
Like
Yeah. No, it's not singular values, right? It's really entry wise, right? Okay. So here essentially we have the number of entries here, right? So it's closer to address, trying to assume structure if we assume that this is small. But really, if you think about it, right, so the number of non-zero entries is probably, well, there's the number of words that appear. So let's say even it's a little bit smaller than P, but why would you add a word in your vocabulary that you don't see as a question, right? But and then it has to be upper bounded by K times P. So really, the dependency is, it's not much better essentially than the bound of Coetal with respect to P, right? So this actually, one of the things I should mention is that the dependency on K is actually a little bit better. Would also try to assume some form of sparsity. That's essentially that the row, essentially if you take row wise, right, the number of rows actually that are non-zero in A are small. They also obtain a better error rate, so with an SA replacing the matrix P. But the problem is that essentially this is typically valid in regimes that assume that the vocabulary size is really quite small. And yeah, so it's quite small. So it's not valid across a number of interesting data regimes. Okay, so essentially our hypothesis was that, well, we have to assume some sort of sparsity, right? And the sparsity that we want to assume is perhaps some notion of weak sparsity. That is to say, we're going to assume that within each topic, the maximum amplitude, essentially here I'm ranking the word frequencies by decreasing order. I'm going to assume that j times this j biggest frequency at the power k is less than s, where k is a number between 0 and 1. So this is just weak sparsity, if you will. This is essentially a link to Zipf law that assumes that the frequency decays, right? And so here we're essentially assuming that the frequency decays at essentially j at the power minus k, essentially, right? And this is something that seems realistic, right? So these fast decay have been observed in text documents. So this is essentially what we're going to try to leverage here. Okay, so the question that we have is, can we propose another estimation procedure that makes use of this type of sparsity and hopefully that yields better bound that are, valid for all realistic parameter regimes, especially when the vocabulary size is large? Can we suggest selecting a way of selecting K? And potentially as bonus, can we actually relax the angular word assumption? So this is also, yeah, I forgot to mention, this is work with my two of my graduate students, Hui and Yete. Okay, so okay, let's get into the method that we propose. So actually what we're going to do is look back at the method by Coetal and propose a certain number of modifications. So one of the first steps of that procedure was this pre-SVD normalization, right? So they divided by essentially the frequency of the words to essentially put words on an equal footing, right? Because to deal with the high frequency heterogeneity that they observed. Now, in practice, this can actually destabilize the algorithm. It can create point clouds that are not particularly good because the frequency are so small, essentially, right? So what we propose here is to actually replace this pre-SVD normalization by maybe a pre-SVD sparsification, essentially, right? So we are going to select an appropriate number of words or an appropriate subset of the words, right, on which to apply our topic modeling. Oops. What just happened? Oh, yes, and the idea is that well, you need to actually, so first you need to show that this makes sense, right? And then we'll essentially see how to appropriately select these the set of words J. Okay. Okay. So why this actually makes sense? Well, our idea again is to select an appropriate subset of the words J and apply topic modeling on this new matrix A tilde, right? And what the first thing we show here is that actually when you apply topic modeling on this matrix A tilde, right? A tilde, the underlying one is just essentially a rescaling of A, right? So intuitively, if you take AJ here, AJ1, for instance, to be approximately 1, right? So there's not much, most of essentially of the mass of the topic. Then essentially by estimating A star J, right, we get a good enough estimate of AJ, right? So there's not much difference essentially. So what is the set J? Like what is an appropriate set J? So here the idea is that we're going to select essentially the elements, the words that have high enough frequency. So MJJ here is the frequency of the word observed in the corpus. And we take this word frequency to be greater than alpha, which is a user specified constant, right? Times square root of log Pn divided by n capital N, right? And so alpha again is a constant essentially that is independent of your data regime. So n capital K, P, and capital N. So typically in the experiment, I will see we'll take alpha equals 0.05 actually, and it works pretty well for us. Okay, so that's essentially the idea behind choosing the set J. Once we have our subset of J words, so we replace, so they do the SVD of this rescaled matrix X. We propose to do the SVD of this matrix G, that is essentially sort of like the covariance, if you will, matrix between the selected words essentially, and that we recenter. So this is the frequency of the different words. once we have this, essentially, so we do the SVD of this, we apply the same type of technique, right? So the same post-SVD normalization, vertex hunting, sort of point cloud recovery, and a final row normalization that's a little bit different because, of course, we don't have to rescale by exactly the same thing since our input is a little bit different. But the method is very similar. Now, it actually looks similar, right? But the proofs are a little bit different, or actually quite different, right? And the results are also a little bit different. So, okay, a comparison of the two approaches. So first of all, one thing to highlight is that potentially our method could be computationally more efficient because we're only essentially operating on a subset of size J of the words, right? So we're reducing the size of the dictionary. It's also potentially more robust to frequency heterogeneity, right? Because we're essentially specializing away the words that are too rare, that are too essentially, that don't appear enough. And we'll see it yields a more attractive error bounds in a variety of regimes. So first of all, what does the set J look like, right? So I'm saying that maybe it's more computationally interesting because we're actually reducing the size of the dictionary, or we're getting rid of a set of words. And by this, essentially, we mean that with high probability, the set of words J is less than essentially this this term here. So that looks like something like K times square root capital N times N divided log Pn. Of course, the minimum of this or P, right? And in a lot of our simulations, we show that this could essentially lead, we typically expect around 10 to 40% of the words to be removed. Of course, that depends on the application, but for a number of reasonable data regimes, it actually, the threshold is quite considerably, right? 10 to 40%. And yeah, in particular, J can be significantly smaller than P if, especially, you have this data regime here. Okay, so that's for the set J. Alpha is it determines the thresholding. So it's more, you can understand, it's a constant essentially, right? And no, if alpha is smaller, sorry, let me just go back actually to here. Okay, so if alpha is smaller, I threshold more. Yeah, but that's just a constant essentially, right? Because that's the way we define the number of words that we thresholded. It's more, I think it's more relevant to look at here, I guess. Yeah, so the way we thresholded essentially was alpha times square roots log, I think log Pn over capital N, right? So if capital N grows or N grows, essentially we end up thresholding less. But that sort of makes sense because essentially you just want to get rid of words that are going to perturb your point cloud. If you have infinite information, you wouldn't necessarily need thresholding, right? That's essentially the idea. Yeah, essentially. So yeah, so that's for the set J. Now, so now let's see actually what error bounds we get. So these are actually the assumptions that we will require. So there's essentially 5 of them. Let me just highlight what they mean. So the first assumption is actually A and W are well conditioned, right? So that is to say, essentially your topics cannot be too correlated, because what does it mean otherwise than to try to essentially reconstruct the topic if they're essentially very much the same, interchangeable. We have some notion that the topic must be regular, right? Essentially, we also need to ensure we need to ensure that the anchor words, there's at least some anchor words here that are selected, right? So our anchor words cannot be too rare and thresholded away, right? Essentially, that sort of makes sense, right? Because again, what is a topic if all the relevant words are very rare? And then we're going to assume for now that we have a good vertex hunting procedure. And finally, it's our sparsity assumption, right? So we just need a couple of assumptions on the matrix A and W, and essentially our sparsity assumption. So, okay, so let's try to see what the error bound looks like. Oh, sorry. So the idea here is actually the main idea is here, right? That I'm going to detail. So let's first try to characterize the error that we're making when we're essentially setting all the word frequency on j complement to 0, right? We're essentially thresholding these words away and saying they never appear. So a is 0 on this j complement set. So here is the estimation error, right? So it's aj complement minus a hat 0. So just the one norm of aj. And so this one norm here essentially behaves like a constant that depends on k here times s times square root log pn over n capital N. And this at the power 1 minus q over 2, where q is essentially comes from non-sparsity assumption, right? So note that this is a little bit better than the bounds we had before in topic score, because the dependency on p here is only through log factors. Okay, so now let's try to put this with the actual estimation error in the set J. So we can actually show that with high probability, essentially, your estimation error will behave something like, well, it's just sum of two things, right? It's the estimation error outside of the set J and the estimation error in the set J. And here, this estimation error looks like log Pn divided by n capital N at the power 1/4. So this is, again, even on the set J, right? This estimation error is like better perhaps than the one that topic score assumed, right? Which didn't leverage the sparsity assumption, because at least we got rid of the dependency on P and just included it as a log term. Okay, so that's for the estimation error. So at least one of our objectives was fulfilled. Now, in terms of the choice of k, essentially we have this lemma that tells us that if we choose k hats to be essentially all the eigenvalues are above a threshold. This threshold is defined as the square root n log Pn divided by capital N times Gn. Gn here is a sequence that essentially doesn't grow too fast, right? Then k hat equals k. Of course, okay, in practice, like this lemma is not particularly insightful because you have to actually choose Jn, right? It's not great. The only interest of this lemma and its practical application is that it tells you that in the matrix G, of which we're doing the singular value decomposition, there exists enough information to actually, determine what a good number of topics should be. So in practice, essentially, what we're going to do is just plot the eigenvalues of this matrix and inspect the scree plots to essentially determine what the number is, right? I would not try to automate this because, again, it's quite sensitive to that choice of Gn. So this is what it looks like, by the way. So if you this is for an example, right? Synthetic example with n equals capital N equals 500, p equals 5,000, and here we're essentially plotting the scree plot, and we see that indeed, there seems to be essentially like a curvature that allows you to actually fix the number of topics. Okay. So let's now move on to actually sort of showcasing the methods on a set of synthetic experiments. So for this first set of synthetic experiments, we're going to simply create topic assignments matrix W by independently sampling from directly distribution. So for each column, I draw from a directly distribution. I'm going to select a set of anchor words per topic and assign them frequency delta. And then for the rest of the words, essentially, I'm just going to use essentially a zip curl. And I'm going to normalize everything to unit norm so that it's an actual topic model. Okay, so what's interesting about topic modeling is actually the data regime is quite complex in that you have the number of documents, the size of the documents, the vocabulary size, and the number of topics. And we have to essentially understand the interplay of all these different parameters, right? So intuitively, if the size of the documents and the number of documents increases, the problem becomes easier. If the number of topic or the vocabulary length increases, the problem becomes harder. So here we're looking at so here on the x-axis is always the document length. And so I fixed the number of documents to 500, and I'm looking at varying different, the number of topics and the size of the topic. So the first thing that we observe is, I'm going to compare, so our proposed method, the blue one, and the original topic score method, the red one. So when the problem is relatively easy, right, so especially for small vocabulary size, essentially, there's a little bit of difference here for smaller documents, but the problem, the estimators essentially give the same result. The discrepancy, the gap between the two essentially increases when the problem becomes a little harder, right? And so, especially as the number of documents increases, And so as you can see, essentially the gap essentially widens here. You also note that when the number of topics is small, both methods actually do reasonably well. It essentially occurs when you're trying to increase the number of topics. For the other methods, so here in purple, light purple, we have LDA. Interestingly enough, right, it behaves sort of interestingly in that as you increase the document length, and that's quite a large document actually, it doesn't seem to learn much, right? Neither does AWR. This is something that actually Coetal also observed in their synthetic experiment. I don't have a good understanding of this from a statistical perspective. As you get more information, the method should do better. You can see that, for instance, LDA here actually did manage in this simpler setting, did manage to learn something, right? So it might just be, you know, a lack of alignment as well of the LDA with the like maybe LDA here is not amenable to essentially handling this high frequency heterogeneity. So the green method, the method by being it tries to leverage sparsity. It's not doing super well here. A disclaimer is that this method actually automatically estimates the number of topics, right? It's in this method, essentially, they fix the anchor words, they recover the anchor words, and then they say that the number of anchor words that they've found is the number of topics. So we don't have a way of directly saying find K anchor words or K topics. And so we have to essentially then align them. And so that's part of the reason why there's discrepancy, I think, in the results that they provide. Okay, so now let's try to characterize the effect of the corpus size. Again, we see that, well, actually both of the topic, essentially the SVD-based methods learn at least as the corpus size increases, but as you can see, essentially our method seems to actually do better when the number, especially as the K essentially is a bit higher. Right? I'm assuming they have knowledge of K. Yes. I'm using the most vanilla LDA, so Dirichlet prior. I am doing variational inference. Yeah.
What's that consequence of misspecifying K? Is this SVM where like it's better to be too big, or does stuff then like rotate off into the
So as we're trying to look at this estimation error, it's not quite clear what estimation error when you're misspecifying K. That's actually a more question. Yeah. Okay. So we specified K here, right? We'll get into real examples where it's a little less clear, I suppose. So here I'm trying to show, okay, so yeah, the effect in terms of execution time, right, which is a mix of, us trying to essentially work on a smaller, essentially a smaller matrix plus maybe some stability essentially of the SVD. We see that typically here, essentially the topics score, so the red method, the computation time increases quite substantially. So this is as a function of the corpus size and the number of topics, but the same thing happens actually. So here, sorry, this came out a little less nicely, but as essentially the dictionary size increases as well, right? Which is what we sort of expect. Okay. Okay, I mean, I'll just skip over a little bit. Something interesting though, is when we really try to essentially vary the number of topics, like what is the, how does even our estimator perform as we increase the number of topics. So this is on a log scale to try to see especially the behavior. For a small number of topics here, both methods did really well with a bit of a gap between the two. Interestingly, a K equals roughly 15. Then essentially the different methods sort of catch up. So the message of this slide is that you should probably, as you go into higher and higher topics, right, a number of topics, you have to be a little bit careful, and maybe AWR actually LDA is a better candidate. So in the interest of time, I'll skip over just the analysis of all of this, right? So we have a way of relaxing the anchor word assumption. I'll skip to the real world experiments because this is perhaps a little bit interesting. So we're starting with an NLP example here where we have a corpus of size, let's say 20,000 scientific abstracts actually, which are in K equals 4 categories. So it's CS, stats, math, and physics. And essentially we try to apply LDA, our method, and topic score. The way we're going to try to see how well we've recovered the topics is by measuring topic resolution, because that's a measure we introduced. The idea here is the following. So you take your data set, you split it in half, you estimate the topics on both halves of the data sets, and then you try to essentially see how well you've estimated them, right? So you compute the cosine similarity between the topics, and the hope is that if you estimated the topics correctly, they will sort of be consistent essentially from one half to the other. So the result is that essentially our method was had a very good average resolution, so better than LDA. Topic score, however, was pretty low, right? It's half of that of LDA. When we look into the reason for that, right, we actually looked at representative words, so the top 10 representative words in that topic. So our methods for, you'll note that, for instance, for physics, we have things that make sense, like energy, model, phase, magnetic, right? So it was pretty nice. LDA, there's a bit of overlap between the two as well, which is, I suppose, it's good. For topic score, though, you will see weird things happening. For physics and statistics, you have essentially, polluted words, right? So here you have essentially Italian words like quantistica, and in statistics you have German words, which I will not try to pronounce. The idea here is that what happens, and we actually, should have, you could say, is an example of what we try to solve, right? Is that some abstracts were actually split between an English abstract and translation in another language, and essentially these make for very rare words. When you plot the point cloud that that you're actually that you get, right, and you're trying to do the vertex hunting, this is what you get for topic score. So you see something that is extremely stretched, actually, right? Whereas for our point cloud, we try to just by essentially thresholding away these rare words, you get something that it looks like a point cloud. And also, if you try to look at some of the words on the edges, right, they sort of make sense, right? You have the distinctive statistics flavor in the top right corner. Here's more physics, mathematics, and CS. Okay, so that was one test. We also tried on the microbiome example, right? So here the idea is that you have samples from the microbiome. So here each sample is a document, bacteria, the words, and you count essentially the number of times that you see your bacteria. It's a very different data regime. So you have very, very long documents, reasonable P, but rather, small N. We also applied this notion of topic resolution. And what we see is that our method actually performs pretty well, again, up until rather maybe topic 18 or so. And then essentially LDA starts performing a little bit better, right? Where our method drops and sort of is essentially identical to topic score. I would be a bit careful in going into very high topics though, because it might be the case that actually the prior that LDA puts on the different topics has a stabilizing essentially influence. So I'm not saying that topic resolution is the holy grail of measuring accuracy, right? But it was something, at least in the absence of ground truth, that we could try to measure. So a topic would be essentially a community of bacteria, right? It's a community of bacteria, right? So the idea is that, maybe bacteria, if bacteria words, it's true, it could be the case that certain bacteria have the same function, so bacteria could be synonyms of one another. That's why they like this type of approach actually in microbiome analysis. Similar story, essentially we try to plot the point cloud. So here we didn't essentially show what they were because we couldn't interpret it, right? But the idea is that we can still look at the shape of the point cloud and see that our point clouds looked a little bit more gathered and amenable essentially to analysis. And finally, I'll show our single cell example, right? So again, another very different data regime. So P equals 24 cells, very, very short documents, and a lot of these different documents. So topic resolution looks actually very good when you look at the resolution, right? For up to 20 topics. Essentially, our method is, and they're all pretty much the same, just a little bit better perhaps across most values of case for than a topic score. And the final test that we did was the following. So we're essentially using a recent method proposed by Fukuyama et al. In 2021 that essentially tries to provide diagnostic plots for looking at, how essentially your model, your topics essentially split as you increase them as a way of understanding essentially the output. So the idea is that here you'd be looking at, this is essentially a Sankey diagram, if you will, right? That looks at how topics essentially split and are recombined. as you increase the K. And what we're looking is for maybe a notion of coherence, like topics that appear consistently across all values of Ks, and refinement. So topics that maybe split, right? So essentially like a hierarchical, splitting essentially of the topics. What we see is that our topics are actually pretty stable and seem to be nicely coherent and refined, right? For LDA, it's all quite good up until maybe K equals 11 essentially, right? Where you can see a little bit more recombination, topic essentially splitting a little bit more. I wouldn't read too much into this though, because I'm not quite sure why you would try to go as many as K 12 topics. At the end of the day, what we see though is that what we recover are individual cell types. And that's not very interesting when we're trying to understand cellular interactions, right? So I think you probably stop much earlier. Okay, so summary and future directions, I suppose. So our analysis essentially was to the point was to try and suggest a new notion of sparsity that had not been necessarily explored in literature before. And the idea is that this allowed us to design an estimator that increases the signal to noise ratio of the word point cloud by removing the very noisy entries. It also accommodates, so I skipped relatively quickly over this, but we have a way of accommodating less stringent assumption than the typical anchor word assumption found in literature. And as we've seen, it seemed to improve error bounds on the estimator and, in practice, provide good estimators. In terms of next direction, so the idea is that all of this was motivated by this, spatial transcriptomic example. And now that we've understood essentially what has been done for the matrix A, we're trying to understand how we can actually reliably estimate the matrix W, so the topic assignment matrix, especially with the idea that we want to do spatial regularization in that case, right? We want to really focus on that. And the idea is that we can actually leverage some of what we've learned for the estimation of A to the topic estimation, right? So you can actually show that there's, you have to be a little bit careful. It's not exactly the same. You can't just essentially transpose the matrix and apply the same procedure because the structure is a little bit different. But you actually gain there's at the end of the day, it's all point cloud and SVDs, right? And so yeah, so that's what we're essentially trying to push for currently, and yeah, so hopefully we'll have something a little bit more concrete to present in a few months. So thank you very much for your attention. Thank you also to my graduate students who were essentially on this project with me. And do you have any further questions?
For your NLP application,
Mhm.
there are some more that it can and also we have like the frequency of documents, but
Yeah.
do not convey like the typical
Yeah.
for that. So have you ever considered to try to remove those words?
So-
or just use the idea as construct the matrix there?
We could. We did remove the usual like stop words. There's a list of vocabulary of stop words that you can remove, and these include like very, very repetitive words. It's true that in this essentially it some some other essentially topic-less word appear, right? We could. That's one of the, but it's an additional essentially pre-processing procedure. It's just yeah, we've just followed the very standard pipelines actually for these topic models essentially, and yeah, interestingly, CAN was not removed. I assumed it would be, but yeah. A question? Yeah.
Okay. Some point when you talked about the theory, you mentioned that using bigger of one was the strongest assumption.
Yeah.
Why is that a strong assumption? Because you meant like any
Well, in the NLP setting, not necessarily, right? And if you really want to push things, even in some of the biological example, not so much, right? Because for instance, suppose you could be looking at bacteria. So it depends on how much pre-processing you want to make, right? But you could have like several thousands of different bacteria. Or if you want to look at genes, right, you could have like essentially like several thousands of variants or things like you could be looking at essentially, right? So it really depends on the application. Essentially, the idea that again, our idea was that the bounds that existed were not particularly good, for instance, for NLP applications, and could also probably be refined in a number of concrete, for instance, biological applications, right? Yeah, and essentially, so that's one thing, and then the destabilizing effect essentially as well. The pre-SVD normalization was something that, you know, even without the notion of P being large or not, right, it does occur quite a bit, and yields essentially estimators are a little bit of, you know,